Okay, I'm going to review what we finished in class today and look at some of the additional problems on here. So we have from section 6.4, finding the surface area of rotation. And remember, before this, we talked about arc length. And this formula that we're going to be dealing with involves arc length. So if we find the surface area of revolution given a function about an axis, considering the curve shown below, suppose we revolve the region between it and the x-axis around the x-axis and wanted to compute the solid's surface area. So you kind of get the picture. We get these kind of vase-looking images, of this side would then come down like this, and then that end would, of course, be there. So, and we are only calculating the surface area, or the outside lateral edges. So we looked at the shape of rotation of a cone where we cut the top off, and it's kind of a good illustration of what's going on here because it's a very tiny section that we're considering, but S is equal to 2 pi r times L, and I think on the next page I showed you where we were looking at the actual formula for the surface area for a cone. If you unfold it, that's what you get, 2 pi r L, where L is that lateral dimension, the length on the side. So we walked through this showing how we could derive the formula to get the integral from a to b of f of x times the integral of 1 plus f prime squared and so forth. So, and then now we're just going to utilize it. And sometimes there's a little trick to recognizing how we're going to set this up, and sometimes there's some manipulations. You can do some by hand, but others you're going to have to use a calculator for. Okay, so the first problem we walked through where we find the region bounded by the parabola x squared plus 1. I had you change the one dimension. I think I had it going from the x interval from 0 to 3. I think I might have had a 1 there, so make sure you change that. And so we have our formula. We find our function, solve for x because we're using an r sub I that's equal to just the x. Instead of the expression, remember we can use the expression square root of y minus 1. There are two ways to do this. So in the first one, where you see the s is equal to, that was the way to write it in terms of x's. You will get the same answer. In the second one, where we let x equal square root of y minus 1, which is the radius, you can see where we have the radius times the arc length in terms of y. Okay, and we derive that. I'm going to pause for a second so you can stop your video if you wanted to. And you can see the work on the side where we have x prime squared, and plug that in. And we get a nice integral of the square root of y minus 0.75. Both ways it turned out to be 117, right? 117.319, I believe, right? Okay, so then going on from there, the next problem we have is where we have the square root of x. And I'm just 2 times square root of x. And you can see that I drew a radius. We're rotating around the x-axis from 1 to 2. So we're getting this kind of cylindrical kind of looking thing where if I put, the same kind of dimensions on this side, you see that we're probably going to get like that. And then here. So it would just be the outside of that cylindrical shape. Okay, so it was a good idea to kind of picture what am I looking at, but in this case, we'll just go right ahead and get what the surface area would be. So we have 2 pi times the radius times the length in our integral, and the interval, of course, is in x's, and we're going to go from 1 to 2 here. So we'll put those intervals up there, and then keep in mind you have to be in x's. Everything in x's. The radius then is the distance that you have from the x-axis up to the edge of the solid. So, or the edge of the area, so L. And so that's going to be 2 square roots of x. And then we took the radius, and since that's our y, dy dx is then 2 times 1 over 2 square roots of x, which is just going to leave us, when we square, the 2's are going to cancel, and then we just square it, and we get 1 over x. So there's our integral. And then remember, you have this square root rule. I passed the 2 out front to the 4 pi here, so I passed the 2 out, and then I distributed the square root of x into this integral. Remember, that becomes then the square root of, recall like your rules, just in case it's been a while, you have an x that goes inside times then 1 plus 1 over x. So that simplifies nicely to the square root of x plus 1. The integral is quite easily done here. Now, I didn't do a u substitution because u was equal to x plus 1, du is equal to dx. I just kept them all in x's, and then I plugged in 1 and 2. It turns out I get that the area, surface area, is then 19.84. Okay. All right. So then with the next problem, I have a function that is solved for x already. So I think instinctively I would probably keep it with y's, although you don't have to. It just seems like it's a little bit easier when you do that. So for that one, I said that the radius is r, and I have the arc length there. And then I come over here to the side and I say r is equal to the function. Then you can see where I place the r inside. And then putting that in the integral, and then I calculate x prime of y, which is y squared. Then squared, I get y to the fourth, and you can see we have this nice integral form, right? So now what I'm going to do is, this is one that you could do by hand. This would be that typical kind of problem that you would walk all the way through. So we get s is equal to, close this out, okay? S is equal to, we have 2 pi. And then I'm going to leave this integral here from 0 to 1 for a second. I'm going to say u is equal to then 1 plus y to the fourth. And then du is equal to 4y cubed dy. So then I've got a y cubed there. I'm going to go ahead and divide by, I'm going to pass the 3 out front. And then I'm going to divide by 4 on both sides of this to give me my y cubed that I'm going to have out front. So I'm going to rewrite this. I get y cubed here, the square root of 1 plus y to the fourth dy. Okay, and I don't have my limits changed right now. They're still 0 and 1, still in y's. But then now I'm going to do my substitution where I have s is equal to, I've got this 2 pi over 3. There's my integral. And my y cubed over 3, remember that's going to get eaten up here with the du over 4. So these two things are going to become here, let's put that in the tail end. I know some of you like to do that, but I prefer not to. U is equal to 1 plus y to the fourth, and then I'm going to have times du over 4. Now u is equal to 1 plus y to the fourth, so if I plug in 0 here, I get 1 for the lower limit. And then I get 2 for the upper limit. So I go from 1 to 2, right? 1 to 2. And it becomes a pretty easy integral, if you will. So we're going to get 2 pi over 12 on the outs, 4 out there. So I'm going to make that pi over 6. So I get pi over 6. And then it's the integral of u to the 1/2 from 1 to 2. I could have probably just done that at this point. Du. So it's pi over 6. Times u to the 3/2 times 2 over 3/2 is times 2/3. So u to the 3/2. And I think I'm going to take a break from the u right now. I'm going to go ahead and evaluate that. I've already changed the limit, so plug it in here. So I get 2 pi, 2 goes into 6 3 times, so pi over 9, right? Pi over 9, and then it's just going to be 2, because that's all of this is simplified now. And then I'm just going to put in 2 to the 3/2, not a nice number, minus 1 to the 3/2, which is 1. And there's my answer. So my surface area is this. And I think it turns out to be something, it's pretty small. I think it's 0.638. And that's what I have down in the key, so I'm hoping that's going to be it. Okay, I'll let you check that out. All right, and so that's for that one. Now, we could have done that differently. We could have done that so that we could change it to a cube root of sorts, but that's kind of ugly. So I stuck with the y's, okay? And it was a nice u sub in there. Okay, now we have the calculator one where we start off, and so I have find the surface area of the curve, square root of x plus square root of y is equal to 3 from 4, 1 to 1, 4. And I'm going to revolve that around the x-axis. You're going to use a calculator to evaluate this one, okay? So I've got S is equal to, the surface area is equal to the formula that you see. And notice I'm in y's. So that means I'm going to have to take my equation, I'm going to have to solve it for y. So I go ahead and do that on the side here down in black. Okay, so I go ahead and solve the equation for y. For y's. So I'm solving it for x, actually. So you see what we get here. There's my y. Okay, my x is equal to my y expression here. And the reason why I need to do that is I'm using r is equal to y here, just y. And then I need an x prime, which is in terms of y, x prime of y. So I have it as dx dy, same thing. The derivative of x with respect to y. and then we're going to have to square it. So we do that down here. I plug it in here in the second step. I'm still integrating from 1 to 4. Either x or y in this case is going to be 1 to 4, so it doesn't matter. You have to watch out for that though. So I have my integral form is right here. So there you go. Or I wanted to show you that if you did choose to do it in terms of x's, what it would look like, because you're still revolving around the x-axis, right? Well, this is your y here. So if I opt for that, now this is dx. These are x limits still. Okay, and then I need to just do the same thing. But you see, you're going to end up with the same derivative. It's kind of crikey when you see this answer for it. I think it turns out to be 60. I have the answer above, I think. So I think the surface area turns out to be approximately 63.36, right? And those are units squared, just the surface area, right? Okay. All right, so there's that one. But though it looks different, it's producing the exact same integral. So you have your choice, which variable you want to stay with, x's or y with surface area. Okay. Then you have this last one. Is this the last one, right? Okay, so what I did is I set this up first. This is a little stretch for you guys. You have not studied what we call improper integrals, but I wanted to throw this at you to see what you did with it. Show that the volume of the resulting solid is finite. Now, notice that I took x. That meant x is going to go to, on the interval from 1 to infinity, x is going to go to infinity for this. So I was going to stretch this so that when you see it, you'll be like, oh, I recognize that. That's not too bad. So if I'm going to do the volume for this, I'm going to have pi times, if I'm going to do the integral of this, I'm going to get -1 over x for the integral. Oh, yeah, pi for that. And then I'm going to need to evaluate that. Okay, so I'm going to evaluate that from 1 to infinity. It's kind of a weird thing, right? So 1 to infinity. This is what we call improper. You have improper fractions. This is an improper integral. So I can't have infinity. If you remember the fundamental theorem of calculus, a and b have to be finite values in here, and it's not. The graph is continuous on the interval from 1 to infinity. You see as it goes out, you have this edge that continues to get closer and closer and closer and closer to the x-axis. But let's read this again to see what we have. If the region on the x interval from 1 to infinity and the y interval from 0 to 1 over x is rotated about the x-axis, show that the volume of the resulting solid is finite, and then show that the surface area is infinite. So this is actually kind of a curious little thing, and there are many things like this, like Cook snowflake has a finite area, but an infinite circumference. It's a very famous snowflake. So when I look at this, I go, I don't know. What we have to do with this is we have to incorporate limits because we're headed towards infinity, but infinity is just an idea. So we can't do this. Let's go like this. Let's go, mathematically, this is an error here. So what we can do, however, is we can say pi, we can say let b approach infinity in this. So we say pi times the limit as b approaches infinity of the integral of x to the -2 from 1 to b. So we put in that literal constant, and it kind of makes sense when you get this. And then this is dx still. So we end up with pi times the limit as b goes to infinity of this expression, -1 over x, because remember, the integral of x to the -2 is going to become x to the -2 plus 1 over -2 plus 1, so you get this. And then you're going to evaluate this then from 1 to b. So that's the way we handle it. Now, if you do that, you see that you're going to get the following. You're going to get pi times then the limit as b goes to infinity. Let me see if I can fit it all in this window. B goes to infinity of this kind of an expression. You get -1 over b, putting that in first, right? Minus a -1 over 1, okay, like so. So what happens to this? What kind of area do you get with this? Well, what happens is when you put infinity in the -1 over b, that thing is going to approach 0. So you're going to get, I'm going to scooch this out of the way temporarily. Here. That guy looks kind of worried. Okay, so then we end up with pi times, we're going to get 0, the quantity 0 plus 1. So your answer here is pi. And you actually do get a finite area as 1 over x goes to infinity. And it gets all the way out there. It gets so very close to the x-axis. And it's said that the area then converges. So we'll discuss those a little bit more. Now, the next one is kind of a curious one. And what I would do with this is, see, now I know that I have this 1 over x squared. It converges, right? Well, I know you have to almost know that this integral 1 over x diverges. Now, you don't know that, so that this part of the problem becomes kind of easy. That diverges as you go from 1 to infinity. That means it never ends. Okay, it's infinite. It produces an infinite surface area. Infinite integral at this point. So we're not looking at that. So now what I would do in a problem like this is I would say, if I know this thing diverges or goes to infinity, and look at the integral that you have here. If I take this and I say, well, the integral I have for s, and I'm just going to call it s here, the same. I'm going to compare it to this. I'm going to put up another integral. I'm going to say, well, 2 pi times the integral from 1 to infinity. I'm going to keep it the same, of 1 over x times the square root of 1. And I want you to consider that because I kept the square root in the integral. I could have just left it as 1 over x, but I think it makes more sense to help you in your thinking. I want you to compare that to the integral that we have up there for s. Is it greater than or is it smaller than? Well, if you look at it, that s integral has the square root of not 1, but 1 plus a little bit more. So as x gets big, it doesn't matter. It's still going to be 1 plus a little more. So that means that s is going to be greater. So let me move that over here. This s, and I'm talking about the surface area that we have above here. Bum, bum, bum. So that's going to be greater. So think about this. For 2 pi times this thing is going to go to infinity. So you have the surface area integral is going to be bigger than something that is going to be infinity. So we're done there. QED, it's going to diverge. It's going to go to infinity. So that means that the integral diverging means it's never going to stop collecting surface area. It's going to be infinite as it goes all the way out to infinity, looking at that diagram, okay? All right, that's a quick review of the problems that we didn't get through in class today, so I'm going to cut out here, and I will see you tomorrow. I hope you enjoyed the homework. I know that's kind of fun to go through. If you need to, look at Larson. You have some links in there where you can look at the Larson site to help you with your homework. All right, and I will see you tomorrow. Have a great night.